Now, there is one more way that we can minimize errors and maximize power, and that is by increasing our sample size. And as a general rule, now you learned this at the beginning of our journey together, that bigger samples tend to yield better estimates. Remember that a lot of estimates are consistent estimates. That is the phenomenon whereby as you increase n, the estimate gets closer and closer to the value in the population. It gets closer to the parameter. So we would expect that bigger samples are going to reduce sampling error, all right? And we can see that when SEM is large, so when we have a lot of sampling error, HO and HA become very fat distributions, all right? So they become more platykurtic, okay? They get fatter. And as they get fatter, they overlap more. And what happens as they overlap more? Well, this area grows, right? And this is the area where we might be making a type 2 error over here or a type 1 error over here, all right? So as the risk of these errors go up, what happens to the probability of making a correct decision? Well, that goes down, all right? So what can we do to help the situation? Well, we can test more people, and by doing so, we reduce the SEM, we reduce sampling error. And what happens when SEM gets smaller? Well, the distributions become skinnier. They become more leptokurtic. So as they become skinnier, there's less overlap between them. With less overlap, we see a reduction in the probability of making an error and an increased probability of making a correct decision. All right. So again, increasing your sample size will reduce the variability of HO and HA, and it's through reducing SEM. All right. So low SEM, low variability, less overlap. Now there is an unfortunate annoyance, I guess. It's not really a problem, although I know I sometimes say it's a problem, but it's more of an annoyance, and that is called diminishing returns. So what is diminishing returns? Essentially, it means that as n increases, you're going to get less bang for your buck. So as we increase n, we will see a decrease in the SEM, the standard error of the mean, but the standard error of the mean begins to drop in smaller and smaller increments. So that's illustrated here. Okay, problem. I knew I wrote that. Okay, so as sample size increases, so that's along the x-axis, you can see that SEM on the y-axis begins to drop, right? And initially, as we go from, let's say, having a sample of 10 to 20, we see a very big drop in SEM. However, as sample size continues to go up, that decrease becomes more gradual. Okay, it decreases in smaller and smaller increments. So over here, once we get to these very large sample sizes, SEM will continue to drop, but by very small amounts. In fact, so small that you're going to say it's not worth it, right? Too much time and energy, too much money spent testing, and you're not getting enough back for all that testing, okay? Now, it kind of then leads us to the question of, well, how many participants should I test? I want to get SEM as small as possible so I can, maximize power, but I don't want to have too big a sample size because then I'm basically wasting my time, right? So there is an app that will run a statistical procedure called power analysis, all right? And this particular analysis is going to determine what your optimal sample size should be. Now, it's a bit of guesswork, but it will give you some idea of how big your sample size should be. And what you need to use or to perform this analysis is you need to select a value for power, So what do you want this probability to be? The probability of correctly rejecting HO. And usually we set it to 0.8 or 0.9. So we would love to have that high of a chance of correctly rejecting HO, right? Okay, so the second thing is you have to estimate the standard deviation for your dependent variable. Now, how do you do that? Well, you haven't conducted the study yet, right? This is why you're trying to figure out how many participants you should test. But you could look at previous research and look at the standard deviation for that same dependent variable in other studies. Now, you might say, well, that dependent variable's never been tested before. Well, okay, but something similar to it has been. So you're just going to have to try and estimate the standard deviation based on prior research. And then the third thing that you need to do is decide what would be the minimally acceptable absolute effect size. So remember that absolute effect size is the difference among your means. So how big a difference do you think the means have to be? All right, how different should they be for the research to be worthwhile, for the research to be practically significant, which means important, all right? Not statistically significant, but practically significant, all right? Because certainly you could get a difference between two means. If that difference is really, really small, then nobody's going to care, right? So that's what this refers to. How big should the difference be between your means for you to care? All right. Now, once you plug those three things into the app, it's going to calculate N, sample size. And that would be the recommended sample size for your study. All right. All right. So that concludes this section.